In the industrial practice, stir tanks are used in a variety of important operations to perform many different processes. The mixing process carried out in stir tanks is particularly important in fields such as pharmaceutical, plastic, and petrochemical. The main purpose of mixing is to provide a proper contact between two or more components in order to optimize the mass transfer and to obtain a product with the specified properties. The first step that was taken was to import the CAD geometry into the STAR CCM Plus program. Both the Rushton and the new impellers were coupled with a standard tank diameter and height of 14 centimeters. There were some geometrical restrictions that had to be taken into consideration. For example, the diameter could not be larger than 5.1 centimeters, and the maximum width of the geometry had to be of 1.04 centimeters. However, both restrictions were satisfied, and the maximum diameter that was achieved was of 4.666 centimeters. After the geometry was imported into the STAR CCM Plus software, a polyhedral mesh was used for both geometries. This polyhedral mesh has the advantage that it has a much more flexible geometry than the tetrahedral mesh, and therefore the software requires less cells to solve the equations. The polyhedral mesh was complemented with a prism layer mesher, which provides more accurate solutions around the boundary layers, which is where a finer mesh is required. This usually occurs in the parts of the geometry that have a steeper gradient, such as the tips of the impeller's vanes, and therefore a finer mesh with more abundant cells is usually necessary to properly and accurately solve the equations. Finally, a mesh with the following conditions was obtained. The boundary conditions that were taken into account were the traditional no-slip condition at the walls of the tank and the impeller. Also, for the mixer, a rotating body motion was used. This is an unsteady state rotation that is superior to a moving reference frame because it models the rotation of a solid instead of using a coordinate system shift. The rotating speed was calculated for different Reynolds at different powers of 10, ranging from 10 to the power of 1 up to 10 to the power of 5. Laminar flow development is much smaller than turbulent flow developments, and therefore the time span had to be carefully considered. The solver iterated 5 times per time. Consequently, the following results were obtained for the Rushton turbine and for the impeller that was designed by our group. These tables show the variables for each geometry that was obtained after running the simulation. The first graph that can be observed in this slide compares the Rushton turbine with the regression equation that was provided. And the second graph compares the CFD data for the impeller that was designed by our group with the regression that was proposed. The RMS calculated in the first graph was of 12.05, and this is in the scale of the power number because it varies from 0 to 100. So we can see that the error is not too large, but it is considerable. However, as it can be seen in the pink square, the error is mostly from the first data point that was obtained, while the rest of the data behaves very similarly to the literature. The calculation of the RMS was done with the following equation. Furthermore, another equation of importance was this one, which was used to compare the behavior of the Rushton turbine. This diagram represents the shear rate of the Rushton turbine compared with the data found in the literature. The blue curve represents the shear rate that was calculated using these two equations. The orange curve represents the CFD results, and the gray curve is another representation of the CFD results, but using the monitor report for shear rates. The gray curve is another representation of the CFD results, but using the monitor report for shear rates, which was this equation. At first, the results are not very satisfying because the CFD results did not match those found in the literature. However, after applying the literature correlation to the CFD results, the ones obtained experimentally were much more similar. This error was caused by the way in which the monitor provided the results. For example, the results were presented as the average of the shear rates, but if the mode or the median of the data had been used, the results might have been closer to those found in the literature. The reasoning behind this idea is that the shear rate stabilizes after nearly half the simulations have passed. So if we use the most stable value that appeared near the end of the simulations, then the results could potentially change. The graph that can be observed here is a comparison between the two impellers that were studied in this project. The shear stress of the impeller that was designed is much larger than the shear stress produced by the Russian impeller. This comes as no surprise because the impeller that was designed was a sawtooth impeller, and these are very good at sharing particles and solids and emulsions, and they're also very efficient at breaking and dispersing clutters of nanoparticles. According to the literature that was studied, impellers can also be classified depending on how much shear they produce. So there are two types of impellers: the ultra shear impellers that produce low power numbers, and the high shear impellers that produce high power numbers. The impeller that we designed is an ultra shear, while the Russian impeller is a high shear impeller. This indicates that the results that we obtained can be corroborated by the theoretical information that we gathered beforehand, because whilst the power number of the Russian impeller is larger than the power number obtained by our impeller, the shear produced by our impeller is bigger, which again was found in the literature that was studied. It's important to consider that this impeller, the sawtooth impeller, was selected because it produces higher Reynolds numbers, and turbine Reynolds perform better at high RPS. This figure represents the velocity profiles that were obtained for each equipment at turbulent regimes, which was when the Reynolds number was at 10,000. The Russian turbine has a lot more pumping power than the impeller that was designed, and also our impeller showed a lot of dead zones and was much more stagnant. This was because the Russian geometry provided better shear and also a better power number. These results demonstrate that the Russian turbine had a better performance than the impeller that was designed. This was mostly because a good shear stress is wasted if the fluid is not moving enough for the shear to be distributed homogeneously. By taking these results into consideration, there are several improvements that can be made on the geometry that was assigned to obtain better results. For example, two impellers could be coupled together in order to remove the shortcomings that were caused by the geometry of the impeller. Changing the fluid would also guarantee better results. For example, if instead of water, a fluid with a higher viscosity, like an emulsion, were to be used, then our impeller would perform better because our sawtooth impeller provides a higher shear stress than the Russian turbine, and that would break the emulsion particles more efficiently than this turbine.